Okay, welcome guys. So today, let's talk about application. So just a simple, some not so simple application of the group homomorphism. Okay, so previous that we already proved the first group homomorphism theorem. If you haven't seen the previous video, that I mean you can check. For my, I will put a list link below. Okay. So just let me just recall that. So our idea is that you can construct so given a group, if you have a normal subgroup n satisfied xn x inverse will be a set n, then this is called normal subgroup. Then you can construct a map from G to G quotient n. Okay, so this map is surjective, and then the kernel phi is just n. Okay, so this is the previous, and also for any group homomorphism from Xn to so from group G to G bar, then you can prove that the G modulo this kernel phi will isomorphic to the image phi. Okay, so this is called the first group isomorphism theorem. Okay, so let me just give a definition. We will not use this definition, but this is very important. The group is simple. Means that there's no proper normal subgroup. Okay, so proper normal subgroup means that there's no subgroup which is not identity and then not the group itself. Okay, and it's obviously that this is not, yeah, this is called a simple group. Okay, so the cyclic group, okay, so cyclic group with prime order is simple. Okay, so for the reason is that there's no proper subgroup. The reason is that let's see. The reason is that if you have a proper subgroup n, then your n must divide by Lagrange theorem must divide G, right? But G is just P. G is just prime number, so n must be P or identity, right? But if it's or one, right? If it's then it's order P, then it must be a whole group is one, then it must be a trivial group. So no proper subgroup. Okay, and I have built a video list. I will have built a video proof that this is the we will use a Sylow theorem in the future to prove that the smallest non-abelian simple group is A5, which is a even permutation of 5 symbols, which this order is 60. Yeah, so this is the so alternating group. So basically, I built a video list to prove this. In I built a YouTube video. I will post a link. I will post a link below. Okay. Yeah, but up to now we still do not send the. That's what is the application. So today we prove the Cauchy applications. So Cauchy theorem for abelian groups. Okay, so what I gonna to prove is that if G is abelian and G is finite, and also P divides G. So basically, G has some prime power P. Then there is this element A, which is not identity in G, such that its P's identity. So basically, you can always find a element in the G which is prime, which is P equals to identity, which in the order of A is P. Okay, so this is just the same as the order of P. A is P. Okay, so we want to prove this. By the way, if you know the factorization theorem of the abelian groups, then you know that G have some cyclic. G can always have the permutation. G can have the decomposition into the cyclic group, right? So if you have some prime power, then G must then G others, then G will have some factor like ZP, ZP cube, ZP, this type of things, right? So you can focus on such things and prove it. Okay, but in this But in this video, we will not assume. So we assume that we don't know the factorization of the abelian group. Okay, so let's see. Okay, so the proof basically is an induction. So induction on group order G. So we assume that any group with order less than G, or less than G is basically let's say N, right? So any group element less than N, any group with its order element is order less than N satisfy this property. Okay, so let's do induction. So induction is basically using the idea of subgroup. So let's say if G is simple, right? If G is simple, and you can easily show that if G is simple, that means G has no subgroup. Then you can prove that G must be cyclic or prime order. Okay, so this is a simple exercise. I mean you can check. So once you have this, then cyclic and prime order, right? But the P divides G, right? So in the G is simple, so G must be a cyclic group. Okay, and if you choose cyclic group, you just take the element 1, right? So which will add P times will be P, right? Okay, so this is trivial. Okay. Okay, so now we can assume that G has some G has some subgroup N, which N is not identity. And okay, so if P, let's say if P divides N, then by induction, right? By induction, we will have the element B. We'll have some element B belongs to N. B is not identity, and the B to the P is identity, right? So this is by induction. Okay. Okay, and since we know that B belongs to N, right? So this becomes B belongs to G. So the proof is done. So if you have a normal subgroup with order P, then the proof is finished. Okay, so let's assume that. Let's assume P will not divide N. Okay. So now we need to use a quotient idea. So now since G is abelian, so N must be abelian because N is the subgroup of G. So we can consider group of G quotient N. Okay. So if P do not divide N, right? But by definition P must divide G. So we must have P divides G quotient N. Okay. So which is less than G. So by definition, we can use our induction, right? So by induction, well, is G. So by induction on G and N, we know that we will have the element. So let's call this element X. So we will have element X in a G quotient N, such that X to the P is E1, right? What is E1? So E1 is identity in G quotient N. Okay, and also surely that X is not the same as E1. So let's and we have XP, right? It's basically identity. So identity in the G quotient N will be just N. Identity. Okay, so let's see the identity in the G quotient N will be N, right? So should be N, and then let's write X to be Bn, right? Because the element in the G quotient N representative can be written as Bn. So let's write it down. So I get Bn to the P will equals N, right? Which tell you that B to the Pn will become N, and so B to the P will be N. And notice that B is not the same as N, right? If B is the same as N, then X will be the identity. Okay, then which by the way, this E1 is just N. So X will be the identity if B belongs to N. Okay, so now finally we get some element B belongs to N and B to a P. B is not the same. B is not in N, but B to a P belongs to N. Okay. Okay, so by Lagrange. Okay, so it seems like Lagrange is a powerful idea, right? So, okay, so we have this, right? And so we know that the b to the p to the n, right? Because this is subgroup n, right? So any element in the subgroup to the power order to that power or that power must be identity. So we got bpn, which is identity, right? So idea is that you already find something which is power n, which is prime or has the order p. So natural is that you get p, you use b to the n, the p to identity equals identity. So you should that c to be b to the n. Okay, so obviously c satisfies c to the p to the e equals to b. Okay, so the final you just need to show. So we still need to show that c is not identity. Okay. Okay, so let's see if c is identity. If c is identity, we tell you that the b to the n is identity. Okay. But if b to n is identity, that means n b n, right? Because b to n is identity will be n, right? And this is b to the n n. Okay. Okay, right? B to the n equals to because I assume that this identity, right? So b n n will be n and the b is b to n. Okay. Okay, but also remember that what we have is what we have this bn to the p is n. So let's say we have b n p will be n. But you know what? You know that p is not divided n. P is not divided, right? So the only possible case is that b must belong to n. Because p does not divide n, right? So there's no way that this can happen. The only way is that b belongs to n. Okay, so which is a contradiction, because in my previous I assume that I know that b will not belong to n. Okay, so which proves that the c is not identity. So we finish our reduction. Whew. Okay, so hope you guys can understand what I'm talking about. Okay, so this is the theorem, Cauchy's theorem for the abelian groups. Okay, so let's see the application 2. So this is also an interesting fact. If you know about if you do not know the Sylow theorem, then this is the simple version. Okay, so abelian groups. Yeah, Sylow theorem is interesting, especially if you for the general group, right? But we almost for abelian group in this video. So if G is abelian group, so G is abelian. So let's write down assumption. And the P is a prime power, and then you have a P divides G. Sorry, yeah, such that P to A divides G, but P to the A plus 1 do not divide G. So basically, tell you that the P is the largest prime power. P, I only care I have at least A as symbol. So for example, G is, let's say for example G is 30. Then for P equals to 2, then A can choose 2, right? Because right, sorry, A can, if it's 60, then A can choose 2 because 4 divides 60, but A do not divide 60. But for P equals to 3, A can only choose 1 because 3 divides 60, but the 3 squared do not divide 60. Okay. If you have this assumption, then G has a subgroup. Let's say n, right? Its order is P to A. Okay, if you know the Sylow theorem, then this is basically the assumption. So actually for any non-abelian group, for any group, right? If you has this property, then you always have this. You always have subgroup which will become the largest prime power. Okay, so this is the first Sylow theorem. But in this case, we only talk about abelian group. Okay. Okay, so let's say if A is 0, or if A is 0 means that the P divides P to a 0 divides G, and okay, so if A is 1, then P divides G, right? So G already have some prime power. P divides G, then by our previous assumption, then G has some element which is prime P order. Order is P. Then we finish the proof. Okay. So if A is 1, then it's fine, right? So we can do the induction. By the way, okay, so let's start the proof. So if P in the beginning that P belongs to G, right? Because A must be greater or equal to 1, right? So you can define S, which is X belongs to G, such that X P to N is identity for some N. So you pick up all the element which is order is prime power, that prime power, left prime power. Okay. You call it S, and you know that so since let me see. Yeah, let me change the notation a little bit. Let me change this to alpha because I want to use A as an element. Okay, so let's say alpha. Okay, so now let's see. So I know that there's also I know that there's an element which A to a P is identity and A is not identity. All right. So this, and I know that A belongs to S. Okay. So which tell you that S is not just identity. Okay. So S at least 2 elements. Okay. So I just want to, so I claim S is that subgroup. So S is a subgroup of G. Okay. Okay, so G is finite, right? So I only check for X is close. Okay, so let's say if you have X P to N is identity, Y to P to M is identity, and you can do the X Y to the P N plus M, which is X P N plus M, Y P N plus M, which is identity. Okay, so this proves that the S is a subgroup. Okay, so for the inverse, you can check by yourself. Okay. By the way, because G is finite, so in order to check if S is a subgroup, you only need to prove the closure. Okay, so yeah, so fine, and then you also, and that's I also claim that S will be the order of S will be P to a beta, where beta is this. Okay. So let's see. Okay, so in order to prove it, let's assume that Q. Let's assume that you have Q which divides S, but Q is not the same as P. So this is our assumption, and we want to prove that there is a contradiction. So you have the element, right, by the application, by the Cauchy theorem of the abelian group. There is a B belongs to S such that a B to a Q is identity, and the B is not the same as identity. Okay, so let's say we have B to a Q. Let's go C. Okay, just for my notation. So you get C, which is the in the S group, in the S, and the C to a Q is identity, and the C is not the same as identity. Okay, so but we know that C to a Pn is identity, right? Because definition. Okay, but we know that Pn and Q are relative prime. So by the Euclidean theorem, you know that you can find some integer lambda Q plus Upn is 1. Okay, so tell you that now C is C1, C to lambda Q plus Upn. Okay, and this is C to a Q lambda, and C to N mu, and this is identity. C to a Q is identity, so identity, right? So we tell you that C is identity, which is contradiction. Okay, so that means no other prime power are allowed, or no other prime numbers are allowed, right? So S must be P to a beta. Okay. Okay, so if now there is a 2 case, right? The first case is that okay, so we know that S is subgroup of G, right? So and then we know S is P to a beta, right? So we tell you that the beta is basically, so beta is less or equal to alpha, right? Because G at most has the P to alpha factor. Okay, so you have these results. Okay, so now Now let's suppose. Okay, so suppose. So there's two cases, right? If B is alpha, then we are done, right? Suppose B less than alpha, then we can consider the quotient group. So I can consider G quotient S, right? Because G is abelian, so quotient is okay. So this is GS. And I know that P will divide GS, right? Because there's an extra factor that there's an extra factor P here. Okay. So that means there's an element SX, right? Just I use X, right? And then S is a basically subgroup. So let's say we have SX. X belongs to G in a G quotient S. We're satisfied S X is not S and XX to the P to N will be S. But I know that S is XX P to N. Right? This is the just write down the same thing, right? And the X P to N, right? But by definition, it's X P to the. So who tell you that the X P to N belongs to S? Okay. So that means what? That means so okay. So now let's see. So we have these, right? But now, so we know that the E identity is basically XP to N to the order, right? Because XP to N is element in S, so it's S order must be identity, which is XP to the N P beta, right? P beta. So P beta, which is XP to the N P beta, so it's XP N plus beta. Okay, so this means X is not just P to N in S, but definition X is belongs to S. Okay, so in other words, this contradicts our assumption. This contradicts our assumption that SX is not XX is not S, right? Because we show that S belongs to S, so XX will be S. Okay, so contradiction. So beta must be alpha. So that means S is what we want. Whew. So difficult. Okay, so let's talk about slightly application 3. Okay, so I think this video should be renamed as the Cauchy's theorem on the abelian group, or Sylow theorem on abelian group. Okay, so suppose you have T, which is another subgroup of G with T to the P to the alpha. So let's assume that the situation is same, but you have another something stupid called T, and the T is not the same S. So it is an assumption, and the G is abelian, right? So G is abelian. So we know that the ST must be TS. Okay, and by the counting formula that we have already proved, I think in the previous video, that ST is just S times T, S intersection T, is P to alpha, S intersection T. Okay, but let's see, right? Let's say X ST is okay. So S intersection T must be a subgroup, right? So it must be P to something. So which tell you that ST must be P to a gamma, which gamma greater than alpha, right? Because their intersection is your S and T are different, right? So their intersection must be less than P to alpha. So you know that. So now you conclude that the ST order has P called P to a gamma, which gamma greater than alpha. Okay, but ST. So I know that ST is a subgroup of G, right? So we tell you that ST is should divide G. Okay, but now the troublemaker, right? Because P is P to alpha, but you say that ST is P to a gamma, right? And the gamma greater than alpha, so which is a contradiction. Okay, so no subgroup T exists. So the result is that that subgroup S is unique. Okay, so this is a application 3 tell you that that Sylow subgroup must be unique. Okay. Okay, so let me just write down the results. So corollary. why this is very hard to make it correct. Okay, so if G is abelian, or the G such that P to alpha divides G, and P to alpha plus 1 do not divide G, then G has a unique subgroup with order P to the alpha. Let me just make this theorem easy. Yeah, so G has a unique subgroup with order P to alpha. Okay, so this is the Cauchy. Oh, so this proof is a lot, yeah, very long. Okay. Let's see. Maybe this is enough for today. In the next video, we will prove the second and third isomorphism theorem. Okay, so hope you guys love this video. Be sure to subscribe to my channel. Thanks.